Hello, welcome to A&P again. We're still in the respiratory system, and today we're going to be talking about how we can control our respiration. So the different respiratory control centers that are involved in regulating breathing. And so before we can do that, I feel like it's really nice to go back and look at pulmonary ventilation, the physical act of breathing. And we want to ask ourselves, what sort of variables can alter how much we breathe? Okay, the volume of air that are entering and exiting our lungs. Okay, but in order to do that, we have to try to define these different words, right? So, the volume of air entering and exiting our lungs is called pulmonary ventilation. So we're going to go ahead and write PV. And we're going to say that PV, the amount of air, the volume of air that can enter and exit our lungs, this is actually going to be equal to two variables. There are two things that can affect your pulmonary ventilation. So you can think of this like a list too. Either a list or an equation. It doesn't really matter. I like equations better because it lets us know whether it is directly proportional or inversely proportional. So pulmonary ventilation, imagine breathing deeper. Did you just get more air into your lungs? Heck yeah, you did. Okay, so pulmonary ventilation can be altered by simply breathing deeper, the depth of our breath. And this here is called tidal volume. We're going to go ahead and abbreviate that TV. Makes it a little easier because most of us like to sit and watch TV, right? So that's the first variable that can affect pulmonary ventilation. One other variable greatly affects pulmonary ventilation, and that is this. Breathe faster. Did we just change the volume of air going in and out of our lungs? Right? So breathe slower. Didn't we just change the volume of air going out of the lungs? The answer is yes. Okay, this is our ventilation rate or our respiratory rate. I like respiratory rate for my brain. Kind of breaks things up, so I'm going to abbreviate that as RR. So there are two main variables that will affect how much air we breathe. Tidal volume, which is the depth of our breath, and the respiratory rate, which of course is the speed. Of breathing. Always nice to take a nice deep breath, slow everything down, give more oxygen to our brains. Now, pulmonary ventilation can occur two different ways. We could either have passive breathing, quiet breathing. This is the breathing that you do most of the time. You don't think about doing it, you just breathe. Or we can have forced breathing, active breathing, right? Everybody force breathe. It's really easy for us to think about forced breathing because the second we start to think about breathing, normally it's forced. Passive only occurs when you're not thinking about it. So how does our body differentiate the difference between passive and active? Our brain. Right? Our brain is what controls most of the muscles of our body, and in the respiratory system this is no different because the primary muscles involved in breathing and ventilation, well, they are changing the thoracic volume size. Number one muscle involved in ventilation is the diaphragm. The next muscle involved in normal, everyday, passive breathing is the external intercostal muscle. And that's really it. If you're passively breathing, when those muscles contract passively, the thoracic volume gets bigger, the pressure drops inside of your thoracic cavity, therefore air flows in from high to low. So what allows you to breathe out? It's simply the relaxation of those muscles. When those muscles relax, the volume decreases ever so little bit, and that increases the pressure, therefore air blows out. active, we bring into play a whole bunch, a big slew of other muscles. So what I want you guys to be able to do is just focus on thinking about volume size. You can go and memorize those muscles list anytime, but to understand physiology, try to get out of the realm of every single muscle that's involved and just say, hey, if this muscle contracts, it increases the thoracic volume size. If this muscle relaxes, it decreases the thoracic volume size. Therefore, changing the tidal volume, because the bigger the thoracic volume, the greater the tidal volume can be. We're making our lungs bigger, right? And it's our brain that controls all of this in conjunction with portions of our body that have chemoreceptors. That have chemoreceptors that are going to detect changes in the amount of oxygen and changes in the amount of carbon dioxide, and they're going to try to homeostatically regulate how much oxygen and CO2 are in the body, because we want everything Goldilocks, right? We want it just right. Homeostasis. If oxygen levels get too high, what do we want to do? Bring them down. CO2 levels get too low, what do we want to do? Bring them back up. Love me some homeostasis. It's one of the easiest things to understand when we're thinking about physiology. And that's what the brain is trying to do in conjunction with receptors down here in the body that are detecting the change in the stimulus. So let's first look at what's going on down here in the periphery, because down here in the periphery we have some receptors that can detect signals. We have those in our brain as well, so don't think they're only found down here. But we have some chemoreceptors that are constantly monitoring O2 levels and acid levels, honestly, not even CO2 levels, but acid levels, okay, down here in the aortic arch. And those are going to send signals up to the brain. They're going to send signals up to the brain. They can go on either side. The nerve that's involved in sending signals from the aortic arch is cranial nerve 10, the vagus nerve, parasympathetic nervous system stuff. The other major group of chemoreceptors out here in the peripheral circuit that monitor acid and oxygen, you'll see not as much oxygen as it does acid, are found in the carotid sinus, right here in this carotid body, same thing. And these signals also go up to the brain, but these are going through the glossopharyngeal nerve. So this is going through cranial nerve 9. And those signals go up to the brain, to specific portions of the brain as well. So let's look at what's going on in the brain. Okay, cerebral cortex out here, diencephalon in the middle, cerebellum back here, and then this is all portions of the brain stem with the pons. And that's what I'm trying to point out here. This is the pons, the pontine structure. And then this back here would be the medulla oblongata. I'm not going to write it in because it's going to take up too much space. Okay, so that region, the bump, is the pons, and everything behind it is the medulla oblongata. And I didn't draw this perfectly. I'm not a great artist, but you don't have to be to try to understand physiology, because physiology is about the function. And in the brain, in the pons, and back here in the medulla oblongata, we have 3 major respiratory control centers. One is here in purple. Okay, that one in purple is called the dorsal, right, towards the back, respiratory group. Also known as the DRG. Below it, this little red circle here is called the, well, towards the front. So this is going to be the ventral respiratory group. Or the VRG. last but not least, up here in the Pons is called the Pontine respiratory group. You've got this all probably figured out by now. This is going to be the PRG. The Pontine respiratory group. So what do you guys need to know about each one of these? Okay, dorsal respiratory group. This is the primary group of neurons, subnuclei of neurons, that's involved with passive breathing. Okay, because these control passive inspiration in conjunction with some other ones, but this is kind of considered the integration center that is going to get information from the rest of the body, from the vagus nerve, from the glossopharyngeal nerve, and it's also going to get information from the PRG. So the PRG is going to communicate with the DRG, and it's going to allow us to have passive inhalation, which is cool. Because as long as this group of neurons is active, excitatory, then you're breathing in. So what's going to be involved in expiration? Exhalation, same thing. What's going to be involved in that? Let's inhibit the DRG. If you inhibit the DRG, then we're not exciting those muscles involved in inspiration. We're not communicating with the phrenic nerve down to the diaphragm. So all you have to do is inhibit the dorsal respiratory group, and that allows us to exhale. What is the dorsal respiratory group really all about? Passive inhalation when we have excitation, and then you just inhibit it, and it will cause us to exhale. The VRG, the ventral respiratory group. Now this gets its nose involved when we need to actively breathe. So this is where we really start throwing forced breathing into the mix. Okay, this is going to start to allow the brain to send extra signals down through the phrenic nerve to the diaphragm, down to the external intercostal muscles for forced inhalation, and then for forced exhalation we can also communicate with those muscles that are involved. Okay, here number 3, the Pontine respiratory group. Pontine respiratory group is now kind of a regulator. I like to think about it as kind of the supervisor. It is communicating with the DRG primarily, and it's going to be changing the tidal volume, and it's going to be changing the respiratory group, the respiratory rate, depending on what signals are being sent to it. The Pontine respiratory group receives signal from the cerebral cortex, from the limbic system, emotions. We know emotions can affect breathing, right? The cerebral cortex, by the way, to go back real quick, remember, that is where, when we force breathe, that signal has to come from our cerebral cortex, from the premotor portion of our brain. What else is going on in the Pontine respiratory group? Pontine respiratory group also has places in it called like the pneumotaxic center. Pneumotaxic center is going to be sending inhibitory signals back down to the DRG to try to slow down the depth of breathing, to slow down the respiratory rate. Okay, that would be the pneumotaxic. The other one, the apneustic, that one is going to be, in essence, activating. So we have 2 different centers even within the Pontine respiratory group. We have one, I'm use a different color because this isn't coming through very well. Okay, one that we have is called the pneumotaxic. In the pneumotaxic center, this is the one that will inhibit. It's inhibitory. So it's going to inhibit the respiratory rate. It's going to inhibit tidal volume in the dorsal respiratory group. The other major one that we have is called the apneustic. Okay, the apneustic center is the one that activates everything. And for those that haven't seen my shorthand before, I with an arrow down, inhibition, A with an arrow up, activation. Pretty simple ideas. And then all of this information gets talked back to the dorsal respiratory group to change pulmonary ventilation. One's going to inhibit pulmonary ventilation. The other one's going to activate pulmonary ventilation. So this really helps us regulate our pulmonary ventilation because why? PV needs to be at homeostasis. PV needs to be at homeostasis. If PV gets too high, what do we want to do? Bring it down. If PV gets too low, what do we want to do? Bring it back up. Everything on the left side of these equations that I write into my lectures, these are what need to be homeostatically regulated. How do we do that? How do we drive the homeostasis? We alter one of the variables that will impact the left side of the equation. Chemoreceptors is what we have left to talk about here. The chemoreceptors, chemical receptors, what these things are doing is they're monitoring chemical levels in the blood, and they're going to alter respiration. They're going to alter our pulmonary ventilation to try to fix problems. What sort of problems with breathing might we have? What sort of problems with breathing might we have? Well, what if there is alterations in the amount of oxygen in the system? We want to be able to monitor the amount of oxygen. That's what some of these chemoreceptors do, is they're monitoring the amount of oxygen in the circulation. What else are these chemoreceptors trying to detect all the time? Carbon dioxide. They love to monitor carbon dioxide because carbon dioxide is so darn important. Carbon dioxide is the #1 contributor to the amount of acid in your body. And so we also want to monitor the amount of acid. Not just acid produced from the CO2, mind you, other forms of acid like ketoacidosis and lactic acid, fatty acids, so forth, so on. But these chemoreceptors are going to be monitoring these three major things all the time, these three major chemicals. That's what those chemoreceptors are all about. Now, there are two major groups of chemoreceptors. One of them is found out here in the periphery, which is what we drew in here. Okay, this is periphery, not central nervous system. So we have peripheral chemoreceptors. These ones are detecting all three of the above chemicals. Okay? Peripheral chemoreceptors are found in what we drew over here. Found in the aortic arch, and they're found in the carotid sinus, the carotid body. Now what they're constantly monitoring, they're detecting all three of the chemicals. The primary thing that they're detecting, though, is CO2. But they also are monitoring the amount of acid that's being produced from, I don't know, kidney function or from your diet or from exercise. It doesn't matter. If there's a source of hydrogens that's not CO2, then these peripheral chemoreceptors are trying to detect them. In addition, they're trying to detect oxygen. But they're trying to detect a very specific partial pressure of oxygen. They are only activated, these peripheral chemoreceptors for oxygen are only activated if the partial pressure of oxygen drops below 60 millimeters of mercury. And by now, we're in a pretty severe state of hypoxia. Okay, so you can see now, maybe you can see now that peripheral chemoreceptors are detecting hydrogens, carbon dioxide, and also kind of oxygen. They're not looking at small changes in oxygen. Your normal partial pressure of oxygen in your blood should be 100 millimeters of mercury. And yet this thing only gets activated if it drops below 60 millimeters of mercury. So you must have a relatively large change in your partial pressure of oxygen before these kick in. The other major type of chemoreceptor is found in the central nervous system. And this is the one that I tend to focus on more in my class. Doesn't mean it's more important per se, it just means that it's what I focus more on. The central chemoreceptors. And central chemoreceptors detect one thing really. They detect hydrogens made by or produced by the concentration of carbon dioxide, or the partial pressure. Let's go ahead and put that. Okay? Produced by carbon dioxide. Central chemoreceptors are constantly monitoring carbon dioxide because your body really, really, really cares about carbon dioxide. Because the more carbon dioxide that's in the system, the more acid is produced. If you go back and look at one of my previous videos, I talk about this, and we can talk about it again here. But CO2 plus water in the presence of carbonic anhydrase, Ca, this combines all of these atoms, all of these elements into H2CO3. That is carbonic acid. I'm not going to write the word down on here. You guys can do it. It's carbonic acid. So again, carbon dioxide plus water plus carbonic anhydrase makes a lot of carbonic acid. So the more CO2 that's in your body, anywhere that we have high levels of carbonic anhydrase, we're going to be making lots of carbonic acid. Where you guys saw this before had to do with the transportation of CO2 by red blood cells. So red blood cells have a very high amount of carbonic anhydrase because it's constantly converting carbon dioxide into carbonic acid. And then what makes this an acid is going to dissociate because there is one hydrogen that has a hydrogen bond to the other molecule, which is bicarb. So this is going to release a hydrogen, and everything that's left over is our bicarbonate molecule. Anywhere we have carbonic anhydrase, we're going to have high levels of hydrogen. Therefore, we have an acidic solution, and we have lots of bicarb being released as well. So where does this come into play with central chemoreceptors? Well, up here in the DRG, and actually everywhere in the brain, I shouldn't just specify the DRG, but in the cerebral spinal fluid. In cerebral spinal fluid. CSF is cerebral spinal fluid. This is the fluid found inside of the ventricular cavities of the brain. Lots of functions of CSF, but we're going to focus on the fact that in CSF there is a high level of carbonic anhydrase. There is a very large concentration of carbonic anhydrase inside of the CSF. So, if we have a blood supply to the brain, I like how I said that, if we have a blood supply, I hope you have a blood supply to your brain, right? Well, in our bloodstream all the time, we have carbon dioxide. So there's carbon dioxide out in our bloodstream. It's getting converted into bicarbonate, but we're still going to have more and more carbon dioxide, especially if you do something like hold your breath. So out here, let's just say we have some carbon dioxide in our blood. Some partial pressure carbon dioxide. As the levels go up, well, we're going to do more with it. But partial pressure of carbon dioxide. Well, carbon dioxide is nonpolar, so it diffuses through plasma membranes really easily, and it's going to go towards areas that have low carbon dioxide concentration, which isn't towards the tissues. It's going to be towards something, because tissues are making carbon dioxide all the time, right? It's going to be towards something that is going to be converting carbon dioxide all the time. In other words, it's going to be going towards an area that has a lot of carbonic anhydrase. Well, what did we say, right? The blood flows into the brain. Inside of the brain, we have cerebral spinal fluid, and therefore we have a lot of carbonic anhydrase. And wherever we have carbonic anhydrase, then we could write our formula. CO2 plus water, lots of water in our CSF, and the presence of carbonic anhydrase makes carbonic acid. And wherever we have carbonic anhydrase, we're converting CO2. Therefore, the concentration or the partial pressure of CO2 inside of something like the CSF is always low. So in CSF, the partial pressure of CO2 is low because of the presence of carbonic anhydrase. Therefore, carbon dioxide levels in the blood are going to move from the blood into the CSF. Everything in the universe is trying to go from an area of high to low. I'll move that to this side. Everything in the universe is trying to go from an area of high to low. Therefore, carbon dioxide moves over here, and then it gets converted immediately by carbonic anhydrase into carbonic acid. And then what? What do we know? Because it's an acid, the hydrogen gets released. Okay, dissociation. The hydrogen now is out in the CSF. So the pH of the CSF is starting to drop as it becomes more and more acidic. What else is out here in the CSF? Bicarbonate. So the CSF has a lot of buffers hanging out in it. Now, as the CSF flows by the DRG has hydrogen receptors. So the central chemoreceptors, what that tells us is that the DRG that has receptors for hydrogen. And if the DRG has receptors for hydrogen, then the hydrogens that are being released here through this particular chemical reaction, through the dissociation of carbonic acid, then those hydrogen levels are detected. And therefore, they are activated. Okay? As you increase the concentration of hydrogens in the CSF, that's going to activate the DRG. Let's think about this logically, real life perspective, right? Hold your breath. What's happening to the amount of CO2 in your blood? If you can't breathe it out, your cells are still metabolizing. The concentration or partial pressure of CO2 is going up and up and up and up. So what's your brain starting to scream at you? It's saying, breathe, breathe, breathe. Why? Because as the carbon dioxide levels in your blood increase, more carbon dioxide goes into your CSF, more of that carbon dioxide gets converted into carbonic anhydrate, and that carbonic anhydrase dissociates into a hydrogen and a bicarb. The hydrogen's detected by your DRG, and your DRG is sending signals all over the place, but primarily down to those lungs to say, breathe, breathe, breathe. We want to increase our depth of breath and increase our respiratory rate to try to fix this problem. I hope that makes sense. That being said, if we look back at the peripheral chemoreceptors, they're going to be doing the same thing. Okay? They're detecting CO2 levels. How? those peripheral chemoreceptors have a high level of carbonic anhydrase. They have hydrogen receptors for all hydrogen. Doesn't matter how that hydrogen was formed. So it doesn't just have to be CO2 related hydrogen. Your brain shouldn't have a high level of lactic acid, fatty acid, ketonic acid. It shouldn't have a high level of it. It might have some low levels but not high levels. Whereas the periphery does, so we have extra special detectors out there for it. And then when oxygen levels get too low, all three of those things will send a signal up to the DRG to do the same thing we just discussed. Okay, if the DRG, if the respiratory rate increases, or if the tidal volume increases, we bring our PV up to try to breathe faster and deeper so that we can maintain homeostasis. This is a critical reflex. Okay? Let's not forget that physiology is pretty much all about homeostasis, and the body is constantly trying to maintain homeostasis. And let's think about this in relationship with a patient. If a patient walks through the door and they are in respiratory distress, if their respiratory rate is extremely high, we know that their body is trying to fix the pulmonary ventilation somehow. You don't know how, but you know some portion of this pathway has been affected in this patient. Whether they have damage to their pneumotaxic center, which would stop the inhibition to the DRG, therefore the DRG is constantly activated. Or what if they had high levels of lactic acid? Then the body wants to try to blow more acid out of the system, so it tries to get rid of more CO2, because as the body gets rid of CO2, it starts to bring those acid levels back down again. We're not getting rid of the lactic acid yet. That's the job of the kidneys. But the respiratory system can try to compensate by getting rid of CO2. All sorts of things we can think about, all sorts of disorders we can think about using the stuff that's on the board here. So keep that in mind when you're studying. Don't just memorize. Make sure you try to understand and learn. If we break something with a disease, because that's what we're after, how will it impact the system? How will it impact the normal physiology? Therefore, what sort of symptoms will we see in that patient? Now, I hope this is helpful to everybody that watches it. That's it for today. Humankind, be both. Hope to see you in the next video.